Welcome back to Math 31. This is the continuation of the lesson on composite functions. And here we're going to look at the applications, which really is what it's all about, the most important thing of this particular topic. So to start off, even though it's applications, let's take a look at a few pretty much standard algebraic functions. We're given f at u is equal to the square root of u. We're given u at x is equal to x squared plus 1, and we want f at u at x. Now, this means that we're taking the u function and substituting it into the f function. So it's a composite function. So if we looked at it the way it is presented, we could replace u at x with x squared plus 1, which is what it's equal to. So f at x squared plus 1 is equal to the square root of u, which is x, replace the u with x squared plus 1, and we get this. Now, there's an issue with how we express this. This is f at u at x equal to this. But you're probably already thinking yourselves that this isn't the cleanest way to express it. And if you are thinking that, that's right. So what I would recommend is, instead of writing that as a composite function, write it as just a single regular function, f as a function of x, and leave out, so to speak, the middle man. It really isn't relevant that u at x is equal to x squared plus 1 anymore. So we can write it directly in simple form as f at x is equal to x squared plus 1. And in fact, this is the way it'll typically be written, unless there's some significance to the u part of the function. Now this next question is based more on that, because here you're given three functions. Y is equal to 2x minus 4 square root, x is equal to 4k plus 1, and k is equal to u squared. We want y at u. Now really, this is asking for y at, if you read on, y at x at k at u. Now that's awkward, although it is technically correct, because we're taking the k function there and substituting it into the x function, and then that x function, now in terms of k, in terms of u, will actually be substituted in right there. And we'll then end up with just y as a function of u, no other variables. So you want to be careful with this one, because x at k at u would mean that we substitute in the k function into the x function. So that would give us x at u squared is equal to 4u squared plus 1. So pay attention to what happened with that. The k, everywhere we saw a k, we replaced it with u squared. And then if we kept on going, that 4u squared is now this part of the function. So now what we have to do is, everywhere we see an x in the y function, so y as a function of u is equal to square root, and everywhere we see the x, we replace it with 4u squared plus 1, and then minus 4. Now, I would certainly advise you to collect the like terms, so distribute the 2 in, so we get 8u squared plus 2 minus 4. So y as a function of u is equal to the square root of 8u squared minus 2. There we have it. So now we don't have to go through the three stages. If we're given a u value, we can plug it directly into the final function. Now on to the applications. So we'll look at three of them. If u at c is equal to 0.8c, if this converts c Canadian dollars into u American dollars, okay, so that's u as a function of c, And K at U equals 7U converts U American dollars into K Norwegian kroner. We want to express Norwegian kroner as a function of Canadian dollars. So in other words, we want to find K at C. Now this really is asking us to find K at U at C. So we're substituting the U function into the K function. Remember with these, pause me at any time, do the question yourself, and then check your answer. So the U at C function is 0.08C. So that gets substituted into the K function, which is 7 times U. So we multiply 7 times 0.8U, and that would give us 5.6U, and that could now be just written, why do I have that U there? It should be 0.8C, excuse me. That makes a little more sense. Excuse the scribbling there. So K at C, there we go, is equal to 5.6C. So this would allow us to take Canadian dollars, whatever we had of them, and convert them directly into Norwegian kroner. We wouldn't have to stop to calculate them and turn them into American money and then into Norwegian money. The next application. A spherical balloon is being inflated. If the radius of the balloon is increasing at a rate of 1 centimeter per second, express the volume of the balloon as a function of time t in seconds. Now, you will need an equation for this. We want volume as a function of time. Now, it looks like it's an innocent enough question, but the problem is we don't have a formula for volume as a function of time. What we do have is volume as a function of radius. On your formula sheet, you may not remember this one, 4/3 pi r cubed. That is volume as a function of radius. But not good enough. We want V at t. Now V at t really is V at r at t. Now the issue is finding a formula for r at t. Now sometimes they tell you it directly, other times no. So we need to work out r at t. Now the radius of this balloon, if you were to visualize a spherical balloon, radius is a distance measurement. And the distance of that radius would be the speed times the time. So in other words, if it's increasing at 1 centimeter per second, it means at exactly 1 second, it would have a radius of 1 centimeter. If time was 2 seconds, it'd be 2 times 1, 2 centimeters. So the distance that that radius covers would be equal to 1 centimeter per second multiplied by the time units. So in terms of a formula, the radius is equal to 1, don't need the units, for every time unit. So therefore r at t is equal to 1t. So that's how you would calculate the radius. The rest of it's quite easy because we take this and we can substitute it into the formula. So V at r at t is equal to 4/3 times pi times 1t to the exponent of 3. And then when you simplify it, I'm going to go directly to V at t. That's equal to 4/3 pi t cubed. And we have it now. So if we ever did want the volume given a certain time, at a certain time, we can now do it. We don't have to stop halfway. Let's do one more. Here we have a stone being dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Express the area of the circle as a function of time t. Now, I would certainly recommend pause me, do the question, and check the answer if you think you're up for it. The area as a function of radius is equal to pi r squared. Now, the thing of it is, again, we have to work out the r function. And you drop a stone into water, and there's a series of concentric ripples that are going to go outward. And in this case, quite speedily at 60 centimeters per second. So if we were to work out, use the distance formula again for this, we would get the distance that has traveled would be equal to 60 centimeters for every time unit, or times the time unit. So therefore, r as a function of time is equal to 60t. So at t is equal to 1, the radius is 60. At t is equal to 2, the radius is 120 centimeters. And then that's all we really need, because a at r at t would be equal to pi times 60t squared. So a as a function of t, 60 squared is 3600 pi t squared. And we're done with it. So again, we can go directly from a time value to an area value. So that's it for now. That's the end of the functions review. The next section is going to be a review of inequalities. So thank you for your time.